This is what. Can you hear me in the back? Okay, great. So, I also not too technical, and I've been worried my talk might be too technical. So, I've tried to, balance it. Let's see what happens. First, I need to explain the talk, the talk title. Doveryai no proveryai. It means trust but verify. So, there was this American president, Ronald Reagan. He heard it during the Cold War, and he, liked it a lot. So, he started using it during his with Brezhnev, with Gorbachev, and even the current American president, Donald Trump, he seems to like it a lot. So he's, you can see from the picture. Okay, back to my normal voice. So this is basically an overview of my talk. Anything which has to do with Leslie Lamport, who's invented TLA plus, tends to get very abstract. But I've tried to balance it, make it more approachable to a lay audience. So I'll see what, I'll walk through some examples about how this system works and where it is useful. As the previous speaker, was saying, they found some bugs in this Ethereum system, and a lot of these Bitcoins got locked up. And that's really the problem with distributed systems. There's no way to, actually verify whether this thing is going to work or not in production. Maybe it'll fail after an hour, after a month, after a year. And systems like these, which are called model checkers and formal verification, they are trying to solve this problem. They have, this is like a long history here, 40 years. Most of the work is in academics. These tools have been developed by academics, and they use them over there, but the industry application has been pretty slow. In this case, there have been some people who have applied it in the industry, as we'll see later on. Okay, and the code for my presentation, I'm actually going to show some code samples, so it is technical. The code for my samples is on my GitHub page, which is down there, and the slides are also online right now. So if you have a laptop and you have Wi-Fi working, you can actually follow me. The other thing to note here is that I have slide numbers at the bottom. So if you have a question on a particular slide, you can just remember the slide number and we can come back to it. Okay, let's get started. So as I was saying, even the previous speaker, there was this problem with Ethereum, the blockchain the Bitcoins got locked up, and that's really an essential problem with all distributed systems, that there are these two properties that researchers have identified. One is what they call safety, the other called liveness. And safety means something bad should not happen. Liveness, eventually, good things should happen. So even in this hotel, which is like a distributed system, there are people coming in through reception, there are guests checking in, there is, food being served. So all those things, you have to make sure those things work together. And that's really a problem even in our computer systems, because machines tend to reboot. We don't know whether clients are failing, succeeding, rebooting. And we draw diagrams like these. This is a finite state machine for the .NET remote authentication system. So on your left, there's the client state machine. On your right, there's the server state machine. And these guys, they have tried to, figure out what requests are going back and forth. And based on that, they write some logic. And but this is, mostly at the design level. And, then you maybe have some QA system which, tries to, do some stress testing of all these things. And then there is, there are all these other FSMs which are being created, like, TCP. This has been around for a while, and it's been well debugged, so we know it works. But if you were to design a distributed system on your own, it would be pretty hard for you to prove right away that it's going to work or not. And the reason for that is because there is this combinatorial explosion. There are multiple actors who are running, and each of them go through various states, and there is really no way to verify whether you have, manually verified whether every state of one system and the other system, they actually, they won't cause any problems in runtime. And the core problem we are trying to solve is, how do you reason about time? This is because when we write programs, we put asserts in various places. We say this variable should be greater than 0, that variable should be less than 0. But how do you reason about time? So, if I'm doing certain action, I want to do certain other action later, uh, 3 minutes from now, or I want to make sure somebody else is not going to do something 5 minutes from now. Those kinds of things, you need some formal theory for that. And that's what these people have come up with, these researchers. So temporal logic was developed independent of computer science. It's been around for, I don't know, 50, 60 years. And it was started being applied to computer science about, I think there was somebody named Amir Newelli. They added all the Greek symbols to, brought it to computer science. And gradually, a lot of researchers started developing systems around temporal logic. So there is now linear time temporal logic, there is branching time temporal logic, there is some other things. There's like a whole theory around it. People build computer systems which actually implement this logic. And so the TLA plus, which I'm going to talk about here, is actually developed by Leslie Lamport, and that's also one system which does implement this temporal logic specifications. There have been plenty of others. I have a slide at the end which shows you the others. And TLC is, the name stands for Temporal Logic Checker, and that's a model checker. So just as when you write a Java program, you compile it with the Java compiler. Similarly, you write a program in TLA plus, and then you can compile it with TLC. And I'll have 2 or 3 code examples later. And this slide is really, the researchers will kill me if I try to explain temporal logic in one slide, but I have no choice. So this is what it really tries to do. Temporal logic tries to codify the notion of time, that you are in a certain state right now. In 10 states later, you need to be in this state. So how do I reason about all these things? I will like chocolate from now on, or today it is hot. 3 months from now it has to be colder. Those kinds of things. These things are called path quantifiers, and when you actually write your program in this system, they take your specification and they convert it to these path quantifiers, which then get applied and get verified, as we'll see later. And that's the Wikipedia link for the place from where I took these examples. So people have tried to make an attempt to make it simpler for other people to understand. It's not all Greek symbols everywhere. TLA plus is itself pretty complicated to write, but there is a simpler variant. It's called pluscal. That's what I'm going to use here. Let's go through. So this is how I got started. Basically, I learned it on my own. There is no Coursera course for this, and I didn't really go to some university to learn about this. But so I read about some general background on model checkers, and I downloaded this TLA toolbox. I read through the manual, and unfortunately, there's not a lot of sample programs out there. But it's sort of easy to understand. Once you get the hang of it, it takes maybe a few days, maybe a month. But beyond that, once you start writing a small program, running through the output, verifying what works and what not, you can continue on that. So it's the TLA toolbox is written in Java. So you download the jar file, and you can you write your specification. It has a TLA extension, and then you can run it with those 2 commands that I've specified at the bottom. So we'll go through these 3 problems, so you get an idea of how this works. So first problem is this child care facility problem. I found it in a book. I was trying to figure out what's like a simple problem to introduce to a large audience, and this problem seemed simple enough. It's about children and adults who enter this child care facility, and you want to ensure that there is always one adult present for every 3 children. Now, how do you model this using this pluscal language? So first thing you have to do is you have to break down what is it you're trying to check. So the things we're trying to check is that the adults can enter any time, but they can only exit if the total number of adults is at least 3 times the number of children in that child care facility. Similarly, children can go out any time, but they can only come in if there are a sufficient number of adults. That's what we are trying to verify. How do you do this in pluscal? First, we have to start by defining something called a process. So since there are 2 actors in our system, we create 2 processes. those of you who are familiar with this ACA framework in Scala, so this is like an actor. The process is like an actor. So I created two actors here, and I'm saying that all these adults, they're going to do the same thing. That's what that process means. All the children are going to do the same thing. The algorithm at the top is my system that I'm describing to plus scale. This is simple enough. Now let's go to the next step. So the next step is I have to write out what each child is going to do. So each child, either he enters the childcare facility or he exits the childcare facility. For that, I need to have something. I need to use something called labels. So in Pascal, a label is like an atomic action. It cannot be broken down. And here the child is going to do two atomic actions. Either he enters or he exits, or she exits. Similarly, and in these cases, I'm going to increment a variable saying number of children is +1, -1. We'll get to the checks later. How do I check this stuff? And the labels are important because TLC internally is going to check the combinations of all these states. So it's going to check, okay, child has 3 states, adult has 3 states, and it's going to try to interleave them and figure out if something is going to fail at runtime, if adult is in state number 3, child is in state number 1. So that's why these labels are important. TLC is going to go through all the combinations and verify them. My next step is I need to check that every child will wait until there is sufficient number of adults. So for that, I need to use something called an await, which is a keyword in the Pascal language. The await means that it's an assertion, so it's not an assertion, it's actually a condition. So TLC will wait until that condition becomes true. Only then it will allow this child process to continue to the next step. So in my first label, I have specified the await, which is the condition that children cannot enter until there are sufficient number of adults. Similarly, I'm going to specify the adult process, just as the child. It's virtually symmetric. There's really not much of a difference here. I use the process keyword. I add 2 labels for the 2 steps that the adults are doing, and I have the await. Okay, so now if I this is really it's quite small. It's a small program. It's about 20 lines. There's some of the stuff I omitted. Now if I run this thing, there's actually a bug in this, which you may not have noticed, but it's going to show up. So when I ran this, the first time I ran this, I got the it failed. So this was my failure. This is the output. This is really the problem with these model checkers. They are designed by researchers and they're not really user friendly. So you have to make some effort to understand what the tool is trying to say. So let's go through this. So what it's saying is at the bottom, it prints this whole backtrace of all the states that you have gone through. So first state is state 1, which is the initial state. At that point, it says at line 6 and 7, if you see, it says number of adults is 0, number of children is 0. The second state is when an adult entered the child care facility. So at that point, number of adults became 1. And the third state is number of adults is 1, number of children is 1. So one child had entered the facility, and now the assertion failed. Now I had to figure out, what was causing this assert to fail. So I went back to my program and I realized I had made a mistake in that await condition. I was checking for number of adults into 3 should be greater than number of children, whereas actually I should be checking for the number of adults after one guy has exited. So I had to fix that condition. So this is what I did after that. So I added a -1 and I ran it again, and then it worked. So it had actually gone through all the combinations that told me that there's something wrong with my program. And this is as I said, it's like a small 20-line program, and I was able to find a bug just in my specification using that thing. And after I ran it, after fixing these bugs, this is what it printed. So if you look at the third line from the bottom, there is this statement. It says 3225 states generated, 434 distinct states found. What it has done here is that it has gone through all the combinations given, let's say 10 children and 2 adults. It has tried to figure out, it has built this whole graph, and it has done this graph search. It has done a depth first search on everything, and it's tried to verify that no child and no adult is in a position where some assertion is violated. That's really the strength of this tool. It has told me that my program is correct. If I were to translate this specification into an actual Java program or a C program or whatever, I'm confident it's going to work because this thing has checked all the problems in it. Okay, so let's move to another problem here. This is the famous dining philosophers problem. It's almost all operating system books. There are 5 philosophers. Each of them picks up one fork, picks up the other fork, eats something, puts down both the forks. Now, how would you model this using something like Pascal? Let's go through those steps. Just like we did with the previous problem, we're going to define a process because each philosopher is an independent actor in this system, so he deserves to be a process. So I wrote process ph in 1 to 5, and so what is my first step? My first step is that I need to wait for my right fork to be free. So I'm going to use this await keyword, and I'm going to say, okay, await until that that right fork is available. After that, I pick it up. This is just normal Java programming or Golang programming, whatever you're familiar with. The next step is I'm going to wait for the next second fork. So I'm going to say await fork. Let me see if my left fork is available. And we don't need to model the eating condition here. We just need to say, okay, after you're done eating, let's put both the forks down. So that is my simple program. And now we're going to, this is how it looks in the Pascal language. There's some other stuff at the top which you can ignore for now. You have to define variables and all those kinds of things. So let's say I run this program. What's going to happen? It's going to fail because it's the famous deadlock. So TLC told me that my program is going to deadlock. And what is the deadlock? So at line 15 it says a deadlock is reached. At line 17 there was a lot of output. I had to I've cut some of it out, but the next slide I have some of that output here. And it failed at state number 11. At this point it says, if you look at the 4th to 9th line, it says PC equals wait second fork, wait second fork, wait second fork. PC here means the program counter. So TLC also prints the program counter for each of these actors in your system. So this is telling me that all the 5 philosophers are waiting for the second fork. Each of them has picked up the first fork and they're waiting for the second fork, and that's the deadlock because nobody else can do anything. So TLC is actually verified that this system will deadlock. Okay, so now how do we solve this? So there are multiple solutions. Tannenbaum has some solution, and there are other people. One of the simplest ways to solve this is you introduce asymmetry. You make one of the philosophers left-handed, whereas the others are right-handed. So let's try that. So what I'm going to do is I'm going to add this initial step in my process. I'm going to say if it's the 3rd philosopher, he's going to swap the left and the right forks, and the rest of the program is the same. Now if I run it, let's see what happens. I again ran it after these changes, and it worked. Basically, TLC verified all the states again, and it proved that there is no deadlock. And if you look at line number 20 down at the bottom, third line from the bottom, it says 19794 states generated and 5619 distinct states were found. So these are the number of distinct states, distinct combinations that it generated using these 5 philosophers doing these 3 steps. It basically, it picked up all the combinations. It ensured that none of them are going to fail. And the depth of the complete graph search, the second last line from the bottom, it says the depth of the complete graph search is 27. So this is what they do. They do a depth first search on the graph, and they verify every state. And there's a lot of optimizations they've put into this thing. They do graph pruning. They check if certain processes are symmetric, in which case certain things don't need to be checked. That's like a whole new topic. That's like a whole new presentation. We won't get into that here. Okay, so this is my 3rd example, and I've added this in order to demonstrate how you would model a communication protocol using Pascal. This is, it's on Wikipedia. It's a very simple protocol. There's like one sender, one receiver, and the sender only sends one bit. It either sends a 0 or a 1. And the receiver is going to then acknowledge that 1 or a 0. The only complication here is that the channel is lossy. So let's say I send a 1, the channel might lose the bit, in which case the receiver will not send me an ACK. So I have to keep resending this 1 bit again until I get back the ACK. And after that, I would send a 0 and then the 1 again. So how would you model this using Pascal? First thing I have to do is, just as our normal programming, other languages like Java and Golang, they have libraries for data structures. Similarly, Pascal also has provided some data structures inbuilt. So there is something called sequences. Sequences are basically a linked list kind of structure, and you can use that to define your channel. That's what I did. So actually this is a program written by somebody else, but anyway, we'll go to that later. So this is, I defined two variables. One is the message channel, one is the ACK channel. In order to add to a sequence, I have to use this append function. In order to extract something from the channel, I have to use the head and the tail. And then now again, just as we did before for the Pascal language, it needs to know how many different actors there are. So I added a process for each sender and the receiver. So there are two actors in my system. One is the sender, the other is the receiver. And what is the sender going to do? He's either going to send a message or he's going to receive an ACK. Similarly, the receiver is going to either receive a message or he's going to send an ACK. This is normal communication protocols, the things we write, TCP servers, clients, whatever. And this is where I'm fleshing out how to express this using Pascal. So Pascal has this construct called either or, which allows it to simulate non-determinism. So either I'm sending out a message or I'm receiving an ACK. And similarly, the receiver is also doing the same. So this either or construct is quite important because it's not found in normal languages, and it allows me to sort of simulate non-determinism. It allows me to tell Pascal, okay, either of these things can happen, I don't know. So you go and check all these things, you go and verify whether what will happen if this happens or that happens. And TLC goes through, generates the various states for those things and it verifies. Now the last step is in this protocol is I need to simulate a lossy channel. How do I do that? Because in this, the channel was a sequence and there is nothing in the sequence itself which I can say is lossy. So what you have to do is you have to add another process which is going to randomly delete messages from either channel. And this will also run at, TLC will also run this third process. It will give it some scheduling time. It will run periodically. It will delete messages. And the way you do that is, again, you say either or, remove either from this message channel or from the ACK channel. Just keep removing some random message. That's what this code does. It does width, 1, 2, length of message channel. It's going to check if there are 10 messages. I'm going to randomly remove some message. So that's really the basic way you model either your communication protocol or your system or your software in this Pascal language. Let's go. So I introduced basically 6 keywords in Pascal through these 3 examples. The algorithm is the main thing which is the system I'm describing. Then for each actor I add a process, and within the process I use these labels to specify distinct states that the process takes. And then I use the await keyword to describe at what point the process should wait until something else happens in the system. And I also use the either or keyword to specify non-deterministic execution. And then I use the with keyword, which is right here, to randomly choose one element out of a set. So at line number 3 and line number 5, I use the with keyword. These are like the basic keywords. There's lots of other stuff that I've ignored, but if you actually just focus on these things, you can write a simple Pascal program. You don't need to know a lot of the math that is behind TLA plus. the system takes care of it. What happens is the PlusCal program gets converted to a TLA plus program when you run it, and then it goes to the TLC, the model checker, and that runs your system. So there's some loss of expressive power with PlusCal, but that's fine for an introductory, somebody who's just learning these things. It's good enough. It's a good enough start. These are some of the people who are currently using TLA plus. The first there was these people at Digital Alpha who were using TLA plus for a long time. They're using it to model their cache coherence protocol, and some of them came and joined Intel, so they brought along those tools with them. And there's a paper by Brannon Batson. It's on the Microsoft website where he describes how they used TLA plus for modeling the cache coherence protocol to debug it. So that's been around for a long time, probably 10 plus years. The second example is Microsoft Cosmos DB. They've used it recently, so they invited Leslie Lamport to give them some tutorials, some talks on how to model Cosmos DB operations using TLA plus. Cosmos DB, if you're not aware, is like a geo-replicated database. It's now available on Azure. And the third example is Amazon. They've used it in a lot of systems, and here it was really Chris Newcomb who pioneered it. He learned about TLA plus, and then he transferred the knowledge to other teams in Amazon. And he has lots of good papers on this. How difficult was it to learn TLA plus? What was his experience like? What were the other engineers who adopted the system? Some had PhDs, some were like fresh out of college, but they all took some time to learn, but they were able to apply it successfully. It's been used in lots of Amazon products, S3, DynamoDB. As I was saying earlier, the problem is none of these specifications are publicly available. So somebody requested Newcomb to release some of them, so he released like 2 of them, and I have a copy on my GitHub repository. The others are not publicly available yet. Somebody had requested Cosmos DB to release their specification. They haven't done it yet. I guess it's proprietary. So let me just, do we have time? Yeah, we have time. So let me just, since we have a little time, let me just show you like the toolbox, which is which is how you run this thing through a GUI. So this was my first example, which was the childcare program that I showed. This is how it looks in their GUI. The whole yeah. Oh, sure. Oh, I don't know about this thing. How do I get this? I have no idea. Anyway, I don't know how to get this fonts up here. Okay. But so you may not be able to read it, but you can see the size of the program is pretty small. It's not. This is the first example, and you can always look up my GitHub page, and you can email me if you have any questions about it. But that's what really it is. It is about 40 lines of code, and I ran it through the command line first. But here we're going to run it through their GUI. So for that, you need to create something called a model. So if you look at this thing, it has the first step is you have to parse the specification, then you have to parse the model. So let's try that. We'll parse the specification first. And what happens is when you do that, it appends the translation at the bottom. So the thing that I showed above is pretty simple, but the TLA plus program which is actually generated is quite complex. And this is like how it looks. And Leslie Lamport had this strange idea. He didn't want to use the AND and OR symbols which are available on a keyboard. So I think the AND is like this and the OR is like the backslash and the front slash, or it's the reverse, I don't remember. It took me some time to grasp it, and I still can't remember it. But so that is one problem, and it's the notation is a little more complex. It's not the equal to's and the not equal to's. Anyway, so yeah, so first step is you have to pass the specification, then you have to pass the model, And then you have to create what's known as a model. So let me delete this model. Let's see, I'll create a new model. I'm going to call it new model. So the model is the thing which is actually going to run in the TLC specification. Now here, if I try to run this, it's going to complain because I haven't set the number of adults and children. So I need to set that. So I have to say, let's say my adults are 2. I'm just going to give a few number because if I give 100, it takes a long time to run. And let's say I say 10 children are going to come into my child care facility. And now if I run it, it's going to run through. This is how it runs. And it ran pretty quickly because the number of adults and children are quite few. And these are the states. So it says no errors. And it generated 3225 states. That's the same number that it generated through the command line. The really tricky part is interpreting the output. The rest of the stuff, it's just they've added a few buttons to the GUI to make your life simpler. If you can interpret the output, I think you can win at this game. So I also added the alternating bit protocol here, but I'm not going to run it because it was taking quite some time. That's the problem with this tool. Because it does such an exhaustive search, it generates this huge graph. Sometimes that graph has to be saved on disk, parts of it. Then that graph has to be reloaded, and while it's doing all these checks, so it can take hours to run. Let me go back to my presentation to explain that thing. Yeah. So, the takeaway is that TLC can find bugs. These things should be more widely used, but they are not. We just rely on, some stress testing, some first testing, all those kinds of things. We rely on some, QA team. We don't really know whether our code has bugs or not. And there's this interesting paper which was released in 2001. It's called CHORD, C-H-O-R-D. It was a distributed hashing protocol. It was published by some researchers at MIT. And the paper was well received. And a lot of systems were built using this CHORD protocol. And what happened is none of the researchers found any bugs in it. What happened is about 6-7 years later, there was somebody at AT&T, Pamela, I think her name is. She took that whole protocol specifications, she entered it into her model checking tool, and she found like 3-4 bugs in it, and she published a paper on it. So until that happened, nobody had actually detected these bugs. People were implementing, happily using it. So that's really the issue, that these things should be more widely used, but they are not. And even Leslie Lamport complains, why don't people use these tools? Because they're available. And really the issue is learning curves. There's a learning curve in learning the language. There's not enough sample programs. There's a learning curve in debugging. You have to go through a lot of output. It's not really built to be user-friendly. And mastery of TLA requires some math knowledge. You don't really need to know calculus, but you need to know set theory, like, there's all these Greek symbols to say, something exists, something is, they're called quantifiers. If you get to that point, we can talk. And I would really recommend going through that 4th slide. It's about experiences of software engineers using TLA+. He's documented like this whole social process of how we got people, teams at Amazon to use TLA+. And there was one engineer who had just started out of school, and he took about 2 months to learn. There was another who had was a mid-level engineer, and he also used these things. Actually, I have it here. Hang on. We can actually. That's fine. Okay, so the code, as I said, is online. The README has references. It has pointers to all these other talks, which should be useful, and the slides are also online if you want to look it up later. I have time for questions, I guess. It's 10 minutes, yeah. Yeah, go on.
Hi, Sandeep. Hello?
Yeah.
Sandeep, so that await condition, you didn't bring any temporal logic there. I mean, let's say I want something to happen, or a timer should tell me try no more. So is there a key word for it?
You want to await for a specific time, not not for eternity. Is that what you're saying? I can go back to the slide. Hang on.
Hello?
Yeah.
Actually, if you just go to one of those.
Yeah, I can go back. 1 second. This one. Yeah, this one is good enough.
Await. So let's say I want to say walk await till it's false, or give up, which is more applicable in case of the protocol, I think, because you understand what I'm saying. So
right. So then,
a temporal dimension to this. Either this condition is true or give up.
Right. In that case, you would use the either or. That is part of the language. I didn't use it here because I wanted to simplify what I'm presenting. But somebody else has also posted a dining philosopher's example using Pascal, and he used the either or construct. He's some professor somewhere, so he had. It's on my. If you go to my GitHub site and you link, I've linked to all the people who have written Pascal examples. So one of them, if you go there, he has this dining philosopher example.
Okay.
He's used the either or construct that you're referring to.
No, thanks. So the other question,
Sure.
That swap function, you wrote it, or it's a part of the
No. I wrote it.
Okay.
It's just you can add functions to this language,
yeah, so that's
which do the things you want.
Thanks.
Anybody else? So while I was mentioning temporal logic in the beginning, but I didn't really have any example which showed how these things look. I have one at the end, and this is what it looks like. If you actually start writing TLA plus programs, these are like the operators you would have to use. Since you're using Pascal, you don't have to worry about it because the translation happens automatically. And the strange symbols, P is basically some path. You can say at least one execution path has this condition to be true. This must eventually come true, those kinds of things. And the other thing sorry, there's a question.
Have you used it for beyond sample programs, like for your own production code so far?
We are planning to use it. Yeah, we are building some kind of distributed system, but it's not
Can
yet
you
ready.
give an example of like what kind of algorithms do you think that you will be able to use?
It would be something similar to what number 3. It would be something similar to what Amazon has developed. I work for a cloud service provider, so we are trying to build some distributed system, and it would fall into one of these categories like maybe DynamoDB or the lock manager. That would be the kind of application. But I think it would have more general use also, even if you're writing a microservice architecture where you have lots of running processes, and if you can isolate the steps in that microservice and you can model what variables you want to be want to have at any particular time, that you could have this all these microservices. You could define each of them as a process with these steps, and you could encode it in this language, and then it would run. It might take a few hours, but it would actually be able to tell you whether your specification is right or wrong. And the other thing I mentioned at the beginning was there's lots of other model checkers. It's not just TLC and TLA. This is a list from Wikipedia that I picked up. They have been developed over the years, in many universities, research programs. You can look them up later. So you're not bound to TLC or TLA. If you find something which is simpler, which serves your purpose, you could use it. The general point is that model checkers are useful. They should be used more widely. Anyway, I hope this was not too technical. Otherwise, next year they might say it shouldn't be this technical. Okay, are we done? Any other questions?